This example is intended to introduce you to the reasons why we refer to the crushers as the heart of a production process. What we're looking at is the table for the HP series of crushers that is a Metso-Nordberg product. You'll see I've got three tables. The first is a ton per hour range at various closed side settings. And we're going to be looking at an example for an HP 400. The second table is an average ton per hour at a closed side setting for the different crushers. And the bottom table is a gradation chart that gives you the expected output gradation at various closed side settings. And just to give you a quick look at how the table works, I will change the closed side setting from 5/8 to 7/8, and you see it jumps over here. It tells you what the gradation at percent passing each of these sieve sizes, and it tells you what the maximum, not the maximum, sorry, the average ton per hour. You see the average here is 343 and the range is 305 to 380. You will see that if I change from an HP 400 to an HP 500, it adjusts the average ton per hour capacity, but it does not adjust the gradation. So with that as background, I've created a little sensitivity valuation example, starting with two HP 400 crushers, both set at 5/8 of an inch, operating at 80% crushing efficiency. Crushing efficiency is a function of liner wear, is a function of feed distribution, and other things such as moisture and normal variability and the material that flows into the crusher. The relevance of the crusher efficiency is that if I put this at 100%, you'll see that at 100% efficiency, the theoretical capability of this crusher is 280 tons per hour. So I'll put that back so you can see. What I've created here then is a three product plant. I'm only looking at the crushers, so presuming screen circulations and all to be the same, so we're looking at an incremental change. At the 5/8 inch setting, it shows no circulating load. You'll see if I change this to a 1.1/8 setting that I wind up with a circulating load. But you see 314 tons out of 393 tons at 80%, and you'll see the individual products, what would be expected to be produced. So I've created what would be expected in terms of tons per actual operated hour for each of the examples, the as is and the target. The target is going to focus on demonstrating the variable that relates to managing the yield of key products. We'll get to that in a minute, but before that, another critical variable is of these hours scheduled run, or what percentage actually run. Let's go down here and see what I've done. I'm showing the result, the percent, determine what's going to be on any individual grouping of sieves. So what we're saying is of the 280 potential tons an hour, theoretically you would see these tonnages being retained on the half-inch product. Well, actually it's the 8s, it's a minus half-inch, minus inch is the 57s, and minus 3/16 typically, but I'm showing it here as a screening's asphalt stone and concrete stone, and then there's the circulating load. You see the percentage here correspond to the percentages up above, and you'll see that both percentages for the target and the as is are the same. So taking the variables that I've just shown you and adjusting them, for example, on the incremental value that comes from looking at managing the heartbeat and the pulse of your process. So going back to the variables I've shown you or described to you, and to show you if we're driving for the key product, in this case I'm going to show you what we're driving for the 57s, and we make a change to the crushing efficiency from 85 just to 85%, just to 5% change. You see, it reduces the number of scheduled hours from 2,000 to 1,882 to produce the same amount of 57s. Pretty significant in terms of valuation. If you take it up another 5%, you're $750,000. Very sensitive issues that if you don't know how your crushers actually performing efficiency-wise, you have no idea that you're losing that kind of value. With the scale system, that value would be seen, or the differential would be seen in the recirculating load, among other things that can be seen in the recirculating load, but one of the indicators would be an excessive amount of return material that comes to the screen and goes back to the crusher again. Putting that back to the 80% for consistency purposes. If we have issues with reliability, and you would think you would if you had a 75% runtime, 85% is the typical target. A 10% improvement in runtime lowers the hours from 2,000 to 1,765, getting you the same 1,500 tons as you had previously, generating this exact same number of tons as with the as-is, but with over $800,000 and less cost. Well, let's go back and show you the combination of the two. So now we're looking at over $1 million. The practical capability of achieving this is very high. There's no expectation when you go into a plant that even a crusher that looks to be fed correctly is actually being managed properly in terms of the settings or in terms of the maintenance. So you're always going to be looking for that point in time where you've got a variance from what you set as the standard or the target. Now let's turn those back again. So we've got a consistent base of comparison. And let's see what happens if we change settings. Now remember, we're doing this driving for the 57s. We could do it for a combination, or we could do it just for the 8s. You'll see the 1,500 hours are required here for both of them. If I turn it to 3/4 of an inch, you see the hours required to produce the 57s. The same amount of 57s drops, and a very significant drop in the hours, scheduled hours, with a very significant improvement in variable cost. We close the setting up from the 5/8 to a 1/2 inch and change the target to the 8s. You see it actually takes more hours, not many more, but it takes more hours because the ton per hour drops. The capability of the crusher to produce material or feed material through it reduces as you close the setting, and again it drops to 175 tons an hour from 280 tons an hour. So the percentage yield is not always, in fact it's not usually a good indicator of what the proper configuration of a crushing system is. It's often misleading, particularly when people are committed to using things like flow modeling as a primary methodology for establishing what targets should be. They begin focusing on percentages. You can get your percentages pretty high, but you over it all tons are what you make your money on, so it doesn't really work so good, does it? So carry it one more step and take it out from 3/4 to an inch. Now you see that it goes up particularly high when we're trying to chase the asphalt product. But if we come back and change the target to the concrete product, again you see even more hours are reduced. There's a point in time when you get the balance and create a mode, and the lookup table I showed you before works the equivalent of what the modes would work. Only the modes would have consideration for screen limits, flop gate, flow direction, crusher settings, and etc. So it quickly becomes obvious that we certainly wouldn't be running at a 1-inch setting. Probably running sometimes at 3/4 inch, and sometimes you'd be running at 5/8 inch. And I just can tell you for fact from previous experience that producing this mix of products would typically result in trying to set the crusher at around a 9/16 of an inch and letting it wear out to 3/4 of an inch, and then bringing it back in and giving you a bias then toward the 57 size. And if you needed 8s tomorrow, you bring it down to a half inch, and you run it that way for a period of time, lowering your rate but increasing your yield. There's a sweet spot. And for this example, it's the 5/8. That's the sweet spot. Once you know that, now you've got the gradation curve that you should be chasing. You can use that to estimate what you should be seeing on your belt scales, and you can turn that into percentages and create targets off those percentages. You can compare the throughput rate to the design throughput rate to begin with, but eventually you do the field testing to establish what the realistic throughput rate is with whatever efficiencies or inefficiencies you have in your process. And that's that example.